I have a history of being a computer scientist, and I specialize in GPU programming. Anything that's really high performance computing and computer graphics is everything that I love to do. And last summer, I just something clicked when I was able to build atoms. There was this new semi-empirical method, extended type binding, that uh it's just like it was so fast and it's so accessible. You don't need a supercomputer. You can simulate any electronic structure, any material, even ones that can be parameterized with molecular mechanics, like gallium arsenide. Ah. And back in my mind, I knew that this leak, I knew a little bit about it. I didn't know they were actually using tripods with a carbon dimer. I just knew they were placing carbon dimers and there was silicon 100 and it was unpassivated. And that was all secret back then. And I was inspired by that, and I took the DCB6 germanium tooltip that was studied a heck ton of times in so many different papers, and I placed carbon dimers on graphene in the simulation. And it took a few days to try to find a graphene build plate that would actually accept a carbon dimer, and then try to get actually one that would accept two different carbon dimers. And I settled on one of them, and I just started placing atoms, and next thing you know, I'm just building and building, and it's just like Minecraft because atoms are the fundamental block that makes up our world. There's something so captivating about that ah, I just kept building and building, and then it wasn't diamond, but I tried to make a tooltip. I tried to place boron or carbon, or silicon or boron or phosphorus dimers, and I couldn't actually place them very well. It was like I tried to sort of make a six-membered cage or something, and it it's a bit hard to get atoms to stick sometimes, uh, which is why I say you need ultra high vacuum in practice to get atoms to stick to something because often it's oxidized and there's just no unpaired electrons for a carbon radical to stick to and bond to. So after that, I I built this giant mess of amorphous carbon with carbon dimers. I went to silicon because I theorized that you could actually build a clean crystal unit cell out of silicon. And I did that, and instantly it hit. Like I had tried to place atoms onto a gold tooltip, and I was actually able to get results. I was able to solve electronic structure. It was very buggy and it kept crashing, but I was able to get some kind of at least van der Waals interaction with like a cluster of maybe 20 different gold atoms in extended type binding, which is crazy because Galaxy 16 and molecular mechanics and all these things that are hyper optimized for the upper P block of the periodic table, they don't support transition metals like gold and tungsten, lead, tin, molybdenum, niobium. They don't support any of those. And extended type binding was really geared toward this leftover niche cases of chemistry that are just not covered by the way things are done normally. And it requires a completely different approach to how you parameterize and how you generalize your algorithms to any compound on the periodic table. And that was just, I mean, that helped so much because I explored a heck ton of tripods. I tried at-train tin, and I even tried with lead, which later I found on research papers you can't really make a lot of useful compounds with lead. The lead to carbon bond isn't even stable. But I did try to go to that part of the design space at one point. But I settled on organotins with a carbon to tin bond and with an at-train underneath. Uh, and I used that as feedstocks for silicon. I learned later that this actually isn't very energetically favorable, but I didn't know that at the time. And I started building atoms, and I got I later learned in organic chemistry is an SN2 reaction, where you have like a tetrahedral complex and another thing that hits from the other side, and all the hydrogens will like flip orientation, then it'll stick. And I did that from the tin on the organotin to the silicon on the silicon surface, and energetically it just stuck. If I went slow enough, it would just hit the surface, and then I slowly go back, and then it stays there, and it sticks there every time. It doesn't go back. And I kept doing that, and um, I just next thing you know is that that video that I made that was had the Alan Walker soundtrack. It was the surface that was all hydrogen and chlorine on silicon surface from the CBN patent, and building inverter mode on the underside of a very sharp piece of silicon, which is flat. It's actually characteristic of most STM tips in the real world is they're not actually atomically sharp, but you can get a very high yield of at least being maybe 5 to 10 nanometers round and a flat surface. And that's all you really need to build atoms. You have tripods that are spaced far enough apart that they don't have a double tip artifact. And these tripods will actually be your atomically sharp tip. Then they will image the very like 10 nanometer piece of silicon or tungsten that you're placing atoms onto. And when you release that feedstock, you get a new kind of tip, but it can still take an image. It's going to be a bit different, but you can still take an STM or Q plus AFM image of the atomically precise thing you're building. And I did that, and then I learned after I did that, I made that video that there were some issues with the tripods, the chemistry, silicon to hydrogen, the SiH or the silane with the lone pair of electrons that's stable. You know, the silicon hydrogen, there's two unpaired electrons. The one that's critical to break the five-membered ring and create the six-membered ring that will actually insert into the carbon to tin bond on the tooltip, and you'll get a non-functioning tripod. So it's physically impossible. Even if it was somehow possible to make, it would instantly destroy itself. And the other one with the tin to SiH3, that one, the energetic loss from going from the carbon tin to the silicon silicon, the energetic loss is like zero point 0.1 electron volts. And I guess it worked every time because it's a barrierless reaction. Like hydrogen abstraction off of a bridgehead carbon, it goes one way to the other, and then it just hits, and it's very small change in energy, but it's the downhill. And that's really susceptible to modeling error because zero point 0.10 EV on a semi-empirical uh, model is that's like modeling error. What if one of the parameters was a bit wrong by maybe a few tenths of an EV, and now the flipped which one is the most stable? So you can't really rely on that. That's a really kind of when you do simulations, you can tell things that are probably correct in the real world and things that are probably not. You can just tell where the simulators go wrong, and I think that was where simulation went wrong. So I tried a bit and I found that silicon carbide, specifically a certain orientation of a silicon 111 surface where the silicon to hydrogen bonds are what's pointing up, you can actually form a five-membered ring with a silicon to silicon bond. And I spent about a week making sure that that reaction works every time, and I could be extremely confident that it's physically possible to make that. And it that five-membered ring did form with a silicon to silicon bond. And next thing you do, you have some protecting groups before you form that ring, some methyl groups around it. And by making those protective groups formed, you can actually make sure that unwanted side reactions don't happen. So that when you take CH2 and you hit the silicon in that silicon silicon bond, you can break the silicon silicon bond, forming a new silicon to carbon bond with a new methylene feedstock. And then you rip that germanium tooltip off, and the methylene will stick to the silicon and not the germanium. And when it sticks to silicon, it forms a pi bond, a double bond. And depending on how you've constrained that, you can actually constrain it so it's already forming a ring that's floating in the air. And then you take a blunt non-reactive tripod with like a non-reactive methyl group, and you force it down and you slap it back onto that silicon radical that was just created. So what you basically did was you took a silicon-silicon bond, you pried it apart, you inserted a methylene, created a pi bond, and then you reacted that silicon radical with the pi bond, and now you have silicon to carbon to a new silicon radical up here. Place hydrogen there. You have a six-membered ring and adamantane cage, and you form a silicon carbide unit cell. I don't need to give a fancy video to explain that. You can see hand motions and me explaining things. It's honestly, it's easier to do than actually to program a whole animation anyway. It takes a lot of time to set that up. When I made that video of silicon on that silicon surface, I probably spent about a whole week or more doing those reactions and catching them on the disk and just going down all the different pathways of this is a dead end, you backtrack, and because you saved it on disk, you can restart, and then you go to a new kind of pathway, and then you go a little bit too far, and then you go back and you try a new path, and eventually I found a way to make the silicon unit cell or whatever product I want to make. And then once I'm done with that, I go and I pick which path I ended up taking down, which path I ended up liking, and then I replay them into an animation. And that animation took several days to set up and troubleshoot and smoke test. And yeah, so all that work is stuff that goes on behind the scenes. You never really see that until, someone explains it like I'm doing now. So that happened. That was this. And right after I did that, I lost motivation to work on that. I tried to do various things. I tried to figure out the problem of ripping a product off a build plate, which I learned is a non-trivial problem. It's, I'm not sure whether you can actually deterministically rip a product off a build plate if the build plate has to be silicon carbide and your product silicon carbide. Rip it off is not going to be atomically precise. And also the other orientation of silicon carbide where it's a carbon hydrogen bond on top instead of a silicon hydrogen bond. I'm not sure that this other orientation is possible to build a unit cell. And I didn't really explore that in a lot of rigor. I didn't really have a lot of motivation to do that. And last thing I did was I started porting my renderer. I cleaned up the code base a lot, and I actually did some really crazy shit with the ray tracing. It was fun, and I think it was an accomplishment what I did. I made some critical changes that will unlock the ability to render millions upon millions of atoms in real time, just like Nanite in Unreal Engine 5. That's what was going through my head is where they had, million billions of polygons in real time being strewn from the disk in dynamic levels of detail, just enough detail that you can see on the screen, and when it's not needed, it's streamed away. And it defeats some of the issues with memory or compute because it amortizes the cost of building this acceleration structure over many frames. And that's what I was building toward. And after I made then one of those critical steps, I knew that the next thing I needed to do was to just rewrite the entire code base, what I had there, from scratch, but supporting Windows as well. And I made some progress on that. I got a basic proof of concept working. And then just like my motivation just like tanked. Uh, and around that time was when I got the AFM at my university working. So that's this. Around the same time was when this guy in China started working on STM and he posted that video. Fun fact, he's actually working on AFM now, and he had a video, I think, in January to February, and another one in April, where he's making an AFM that's also 3D printed, based on the AFM workshop one, and he got some like initial tests. I didn't fully understand it, didn't fully watch the video in too much detail. It's all in Chinese, but yeah, he's doing that, and um, I was just like trying to understand all the costs of all this. Like, why can't I do it? Why does it require liquid helium? Um, can you just do liquid hydrogen? Like in nanosystems, theoretically, you only need to get down to maybe 80 Kelvin, and then quantum effects make heavy diminishing returns. So I tried to figure that out, and I talked to some people, and I got some good advice that liquid oxygen is very, very bad. You don't want to mess with liquid oxygen, and liquid hydrogen is, well, it might be cheaper, but it will explode in your face, and you want to be safe and be alive like working with this kind of stuff. So yeah, liquid hydrogen, I don't think so. I kept reading more into this and trying to understand, why can I make this a bit more accessible? Can you do without ultra high vacuum and cryogenics stuff entirely? Just room temperature, ambient pressure. Can you just do that? Well, apparently you can't. You need at least ultra high vacuum. You can't do it with a diffusion pump, which gets like 10 to negative 8 torr at best. You need to have a turbo pump. That's the bare minimum of cost, which is several $1,000s to build any atoms. that'll stick to a non-oxidized surface. I didn't do a lot of research into the electrochemical stuff in solution. There was a good patent by Eli Rabani about making magnesium oxide in solution, but the issue is a throughput bottleneck of clearing out the entire solution and putting basically we're going from acid to base and acid to base over and over again and cycling that, or whatever happens in biology as proteins are built into a one-dimensional chain. But there's an issue that it's an actual chemical reaction happening in bulk solution and it's going to be slow. January, I was reading a paper from around 2014 where they placed atoms onto a metallic surface at around 4 Kelvin, and they were having all kinds of error rates and using these complex computer vision algorithms to try to correct for it. But computer vision is like it solves a symptom but not the problem. So I'm a bit skeptical about people using AI to try to solve the issues with drift and nanopositors not being accurate because AI is such a function approximator. It can be really good if you give it a lot of data, but all it does is map input to output. And if your input is messed up, eh, you can't fix it by just post-processing it. I learned actually the quantitative model for piezo creep is the natural logarithm function. What I found next was that another very thorough paper analyzing different materials, and I found lithium niobate was a very promising material. As was explained in the patent by this wonderful researcher who also does stuff that's open source, um, it can actually cut away a lot of the complexity and all the crazy solutions that were used to try to solve piezo creep. I found in the Art of Electronics, the X chapters, that there was a whole chapter where Horowitz and Hill they read all the papers that I read about charge drives, and they actually perfected the charge drive in Art of Electronics in around 2020. And it was like they were using it to image a blood cell, and when they got a sensor, when it tripped some kind of signal, it would take like 10 images in sequence, and they would have a piezo that moved the camera across like 10 microns. So they moved it basically across, they moved the focal point basically across the entire blood cell, and they took an image as it like they took an image of it as it hit, and that's the application they used it for. Some very, very clever people doing crazy things with electronics. Um, Yeah, so it's very promising because lithium niobate cuts away with all these complex electronic mechanisms that people try to use to overcome piezo creep. Yeah, I ordered them. I got on the phone with a few suppliers and I tried to find the best supplier and I ended up ordering this. It's about $130 for 10 piezo plates, which is a really good deal. And it was already in stock, so I didn't have to wait. But I ordered it because I wanted to make sure that I got it before anybody else did. Because if I don't get it, somebody else is gonna get it, and then I'm gonna have to wait 3 weeks. So that was my mentality. I wasn't actually able to use these, but it's something like first come, first serve. So the major issue with lithium niobate and why I think that it hasn't actually been done yet in a scanning probe is the fact that it has 10% the piezo constant of PZT. And that's an issue because there's a certain amount of range you need to overcome around 20 to 50 nanometers. That is like a critical range that is necessary to overcome static friction in the coarse nanopositioner. So if you want to have a coarse step, it's going to need to be at least more than 50 nanometers to actually overcome friction. And when you try doing that with only 10 piezo plates, remember I was going to do the entire semester with only these things. Uh, you need very, very high voltages, and you need like three different stacks to get kinematic mount to, approach the tip to the surface before you even do the like the scanning. And I got hit with trying to explore the design space of control electronics with this kind of constraint, and I kept running into issues. Yeah, so my design goals were not to build an STM. They were just to try to get that approach the tip to the surface without piezo creep interfering with it. Uh, I was told yesterday that this bottom point is huge, probably based on how I phrased it, but I think it is because that's what I was going to try first was the IZ spectroscopy. So one of the first things that you're told about scanning tunneling microscopy is when the tip approaches the surface in a tunneling regime. the current will increase a factor of 10 for every angstrom it goes forward or backward. And you can have a set point current where you basically have that fixed current, and you can detect the distance based on the logarithm of the current. Apparently, you can't even do that at room temperature, and there's multiple factors that might contribute to it. Thermal drift, but I think piezo creep might be one of the reasons you can't do that at room temperature. I've seen a book where someone did it at 4 Kelvin, uh, but I think piezo creep has been a problem that's been with us since the beginning, and it's been completely under our noses for the entire time. And what CBN ran into when they formed their company and did all this secret nonsense is they got hit by the problem of piezo creep, and they tried these outlandish things to try to fix it. I think I identified the problem. The reason why we had this alarming number that was like a world-ending number, because if you can't get better than this, then you can't build anything complex enough to build other machines. You can't build something with enough atoms to move other atoms and replicate. It's just not possible. So this needs to be solved before anything else. And this is today. This is as good as it is today. Lithium niobate hasn't even been proven yet. It's promising, but it hasn't even been proven yet. So this is as good as we can ever get today, and it's horrible. I mean, it's even worse than we thought scanning probes were. All right. So how do you approach this? There is a very large unexplored design space. This is a very new discovery, and I systematically explored the design space. I wanted to maximize the voltage. And I think it's possible to get possibly up to 1,000 volts. The limiter is dielectric breakdown of air. When you have 1,000 volts over 0.5 millimeters, first of all, that's going to depole PZT. It's going to destroy its polarization for the piezo. But lithium niobate is a tougher material. It can withstand higher voltages, which partially makes up for its lower piezo constant. This is not easy in practice, and it's actually dangerous. Again, I said earlier that you want to be safe when doing things. It's going to be unavoidable. You're going to have to make a custom high voltage power supply, and you're going to have to be very careful to be safe and not shock yourself. The other thing was okay, so high voltage stuff is you don't want to do this for a university project this one semester. It's kind of it's out of scope, really out of scope. So why can't I just make a capacitive displacement sensor? Shouldn't be that hard. Yeah, it's hard. Piezo-stack fabrication, another thing that's out of scope for this semester. Lithium niobate is possible in theory, which was what I was trying to prove. I never said I was actually going to do it in practice this semester. Uh, I think this little interjection tells everything you need to know. One of 5 different bullet points of not pleasant things about fabricating real world stuff. This has been done before. I've seen a paper that's open source about making a shear stack that's vacuum compatible, and they had electrochemical etching, and they glued these piezo plates of PZT with these electrodes, and they detected it with a capacitive displacement sensor, uh, and it had like microns of range. And I could do something similar if I had enough time to sort out all these little details. If you even want to measure these displacements, you need vibration isolation. Like the reason that scanning tunneling microscopy is stable, I think you might need that even to measure maybe 10 nanometer displacements. You need this hanging pendulum of with like eddy current damping of uh yeah, all the things that are in the video from MechPanda. I thought CNC aluminum was a little bit better than 3D printed carbon fiber because it has a bit of better material properties. Mhm. Um, yeah, so that's why I got into CNC machining later. Kinematic mount is also necessary for coarse nanopositioners. They'll quote commercial linear slides and some other commercial products for trying to do like coarse actuations. They aren't stable. They're over constrained and they have strain. Whenever you move something, it causes strain. And when you try to like take a step, it'll release that strain and it'll like move something, it'll jolt like 50 nanometers. So yeah, you got to be careful with how you actually design this. Kinematic mounts are a concept in optics, precision optics, to get deterministic placement and to not have these silly kinds of jitters at the nanoscale. And that requires epoxy too. And that requires three piezo stacks. And that's what people use for ultra high vacuum. I haven't seen anything except kinematic mounts be used, or extremely flat and weird tolerances for like legs of stuff that has range and then hundreds of nanometers of range. You can have some other weird designs. Looked all the way at the beginning of STM and stuff like Binnigan Roar and some of the other early STM designs, and they had some really weird walkers. Sort of like that redstone attraction in Minecraft that picks up its leg and walks. It's exactly the same concept, but with piezos. Electronics is not easy. It doesn't like to work with you. And if you want to have a very sensitive sensor, all kinds of things are just going to not be in your favor. And it does require a lot of planning and understanding how to really maximize performance, which is why it's really hard and takes time to reach very high performance in analog electronics, and to both simulate and then to test and then to validate that the performance you expected is what you got. Multiple design iterations are probably needed to get all the electronics, the actuation with this high voltage, difficult piezo driver, and the current incapacitance sensor to just measure these small displacements from a material that doesn't have a lot of nanometers per volt. Now let's get to things that I actually did. That I can say that, yeah, I did this. I studied Dan Berard's stuff, and I have learned FreeCAD, and I did a finite element simulation, and I calculated the eigenfrequency of that design. I don't remember what it was, but it was in the kilohertz range. I also tried to make improvements to an open source paper. This is a paper about where they analyze all the problems and issues with transimpedance amplifiers and all the things that you should know that are going to go wrong so that you know and you don't make the same mistakes. And then they use those constraints to make a really good, well executed design with three different stages, three different op amps. It was really complex, but I think that complexity is really needed if you want to milk performance out of this to get the best current sensitivity. And I did a lot of calculations and I thought of a simpler variation of the design that would be a bit easier to fabricate. And its current would be in a little bit different of a range of maximum minimum values. And also, it doesn't require high voltage electronics. And I calibrated it. These are three different knobs, like this one, this one, this one. These are all potentiometers that I calibrated in simulation. It's an iterative process that requires multiple attempts. You sort of have to develop a rule for you tune this knob first, and then you tune that knob, and then you go and you refine it, and they interact with each other. So you sort of have to tune. Um, but eventually, I could get this kind of response that was just like the one in the paper. I was not going to be able to finish actually do that in practice by the time that I left, so I decided to start doing. It was about a month left in the semester, and I decided to just go forth and build things in the lab, get experience with reflow soldering. I did that. I got a reflow oven, and then next thing I did is, I went back to the hand soldering and I started the basic soldering board and it worked, and then the intermediate soldering board and it didn't work. And then I found a way to debug this, which is a continuity test. And actually, I think one of these leads here was not soldered properly, and I fixed that, and then it worked. It's rewarding to actually build stuff in the real world. I did this too. This is actually, I used mechanical calipers to measure this, and I sketched on a piece of notebook paper, and then I taped that to this. And then I got the old Windows 7 machine working with proprietary CNC software from Denford, and I got it working, and I seized control of the low-level G code. uh, I like to do things like that in computing, take control of the assembly language at the lowest level, and really understand what's happening at the lowest level, so you can get the best out of it. And that's how I take CNC machining. it's a file of just D code, and I know how to write that. And I got it to calibrate to move to this corner, and then it drilled a hole. The next day, I drilled a hole and I moved through milling out a line of material. And I'm working on maybe getting this one working as well, but it's in a different room. No, the people at the Amp Lab are really kind in allowing me the opportunity to work on this stuff. Uh, the tool bits for this thing don't fit into this one. I learned that. We actually tried. I took this one out, and I think the lubricant isn't that bad, but I took it out and measured it, and it was actually it was wider, but also it wouldn't fit into the chuck that holds it. Um, yeah, so I might end up working on that. I think I'll be able to get it working. I needed a break from the lab after doing that, and the next day I was on a Zoom call with my English teacher about um uh semester, and the English class took up a lot of time this semester. I thought I'd have a lot more time to work on this, but that English class was it was definitely getting my money's worth out of university, and it's rewarding. I think um I got something really valuable out of that. And this teacher, he saw how hard I was working, and it was reflected in some of the poems that I wrote. One of them was titled "The Way of the World," if you can guess how that feels. I wrote some. I was really fascinated with semiconductor manufacturing. One of the poems I wrote was about, a semiconductor fab, and the story that I wrote for English. It was funny, and it was definitely growing as an artist. I needed a break, and I went straight to this PC, which it's a hand-me-down. It's a Windows PC, and I just picked up where I had left off at the very beginning of the school year. And I do have a passion for this. I'm not going to throw away my desire to do this. The last few days, I've been just most of my time has just been spent on this, having fun, learning DirectX 12, the low-level GPU stuff, fixing some of the problems where I left off. I got DirectX Shader Compiler, which is open source. I got that working. Got AMD Fidelity effects. They're all compiled. I have a script I can download DirectX Shader Compiler and Fidelity effects in this Swift package like workflow. I got that script set up, and I got some DirectX tutorials working. Yeah, so I've been having some fun with that, and I think I'm going to continue doing that. It's going to be a very long time until I get to build atoms in the real world, and I think it's extremely valuable. What I did last summer, that experience that I went through just building things like it's Minecraft, it's so accessible. You don't need a supercomputer. You don't even need a GPU. It doesn't even, a GPU won't even help. It's, it's semi-empirical quantum mechanics has gotten so advanced that you can get really high quality simulations. And I mean, that's really what I wanted to do this entire year, was to do that, but in real life. And unfortunately, it's going to be a little bit longer before I do that. But I think I don't need to go to some like Zyvex or some of the other university professors who have been at the Foresight talks. I don't need to go to any of their labs to get access to ultra vacuum. I can build it in my own garage, maybe. Or at the very least, I can build Lithium Niobate nanopositioners and have a heck of a lot of fun doing that, solving critical problems with scanning probe technology, and then see where it goes from there. And for a lot of reasons, ultra vacuum is just hard to build by yourself, not just because of the cost, because of I could go on for days talking about all the issues with doing it. But I think ultra vacuum, not high vacuum, but ultra vacuum is really probably going to be needed to build any atoms at a reasonable speed. I explored a very uncharted design space. This is new territory here. We are really in a new era of scanning probe technology that has never been we've never been here before. And I think that 3 reactions per day at CBN actually was a problem that's been here ever since Binnig Rohr. All the way back then, I theorized that the need for the proportional integral control loop, it's an unproven hypothesis, but just like anything with molecular nanotechnology, it's also just hypothetical. Maybe you can do without the entire feedback loop and just have less restraints and less things slowing you down. So where we're at right now is like EUV lithography, where they settled on tin as the element for the laser source after years and years of research. And once they figured that out, then it was the practical issues with 50,000 drops per second. You shine one laser pulse, and boom, It's like a disc, another laser pulse. Now it's plasma. I watched an agenometry video yesterday where they're trying to do three laser pulses. After, maybe 10 to 20 years, they were like, maybe we can do three laser pulses now to try to improve it even a little bit more to milk that tiny bit of performance out of EV lithography. These are the kinds of things that we will need to do to make nanotechnology happen. The hardware is not easy, but I think the physics works out and it is possible. There's some things that I don't like. I like having control over what's going on. I like being able to optimize and milk performance out of things. That's what I've done with GPUs, and that's how I accomplish things like metal flash attention. I was hired for one summer to just execute things well. And I think what I did with Malflex Attention, I'm really proud about it. And I'm going to use that model of runtime shader compilation in whatever I do next, because it really is flexible. You can hard code things like problem size into the shader. Sort of what OpenMM actually does is they hard code the atom count in the simulation and they compile it at runtime, and that allows certain kinds of optimizations. And I think in GPU code in general is that model of you construct hierarchically you construct the shader and the problem size, like the atom count, will define some kind of optimizations that are done in the driver. And they really the only way to do that is just bake it in the shader code at runtime. Yeah, I want a bit more time to understand electromagnetic interference. I want to use my skills that I got doing FreeCAD and KiCad. These are wonderful open source programs. I want to use them to try to tackle electromagnetic interference. Um, I was on the GitHub for Elmer, and I was trying to get Elmer working on Mac. Uh, and there was a GitHub issue that I was on, and someone supposedly got it working on a recent version of Mac OS. So I have to check that out. And if so, I can use electromagnetic field solvers and FreeCAD integrated. Just works. Often, an important part of simulation is, does it work at all? It may not work the fastest, and there may be some kind of overhead to actually make and design and test code and get it to reach optimum performance. And sometimes you have to accept suboptimal simulation speed and trade off for the fact that it works at all. You can get the job done. It works, and you're happy with the results. And if that can work with finite element method, I think that's good enough. Um, yeah. Also, giant rooms full of electronics like the ENIAC. This is scanning probe Adam doing stuff today. It's literally racks full of boxes for a function that could honestly be done in software. It's so ridiculously bulky. It's like the way people make computers in the olden days. And we got to move forward to the future. We got to make this stuff more compact, easy, less proprietary, remove the sheer number of control boxes. This is silly. Like, look at the electronics for this. Let's do away with the user interface and just code it all in the teensy. Why can't you do that? I enjoy doing that. I enjoy making it smaller and more accessible, easier to hack and modify and do at home. That's what I want to do next. I just want to have time to just go and to have fun and to make electronics and mechanical stuff the way that I think is fun and accessible. I've been getting the skills needed to actually do that this last month. I've been away at the lab. Actually, I still haven't gone back yet after that like game changing day with the vacuum system. But yeah, I think I'm gonna actually go back to that and get a little bit more experience. Finish off, finesse the education in the lab skills to how I actually assemble PCBs because I don't know how they're gonna be assembled. Maybe they're done at PCB Way, or I watched a whole YouTube channel about Z-axis and how they mass produce surface mount circuit boards uh, with electrostatic discharge precautions everywhere. And like these $1 million machines that just back produce medium volume PCBs. I watched the entire channel's videos. They're all like 5 minutes. Some of them are really fun. I watch the Christmas videos that some really catchy phrase of jingle bells, but all of them are the lyrics are about circuit boards. And also CNC machining. I watched like half of the channel Titans of CNC. I watched like half their videos. And then I got experience with an actual CNC machine. And I can't do aluminum or steel. And steel is really hard to CNC machine compared to aluminum. Uh, you might want to have carbide tool bits. and they wear out every time. You have to replace them. Epoxy, I actually didn't do this in the lab. I talked to someone and they didn't have epoxy there. That's something interesting about solder paste, as it needs to be frozen, like in a fridge. The solder paste you use for surface mount stuff, and so are some kinds of epoxy that are pre-mixed. I watched the channel about epoxy technology. I watched some of their webinars, some of their hour-long webinars about epoxy and how to do it in practice. It's not simple how they use these to assemble optical systems. They really use epoxy to bond parts, just like in the kinematic mount and the piezo stack, and they use it to bond parts in a deterministic way. And sometimes it's really hard to do that, just to assemble your own precision system. And vacuum hygiene, I think, is also a really important thing. And just getting some lab experience with, you need to have gloves. You need to wash off something with nitrogen. You need to, if you talk near it, water droplets from your mouth will transport to your sample, and you don't want that to happen. So it's encouraged to not talk while you're handling samples before you put them in the vacuum chamber. Also, when you're moving things between chambers, you want to do it fast. You want to like crank that lever fast to open the door and put it in, and then crank it back so the pressure doesn't rise really fast. This last line, I mean, it's so doable, but it's if I feel like doing that only is going to be a bit boring because it's going to be a bit long time until you can actually get a deliverable, and that's not really fun. Just like it's more work. You have to, well, I want to do this. It doesn't require a lot of funding. I'm not even, that's something not even my concern right now. But my concern right now is do I even understand the hardware and the practical issues? It'll take some time to read up and to just understand how to do this right, to not make silly mistakes, and to not waste a lot of time. If you read this toward the end, it gets a bit funny. And one of the things that I wrote, complexity is the nemesis of progress. That couldn't be more true. I think that really sums up, well, a lot of things. That's the end of this. Hopefully, the phone didn't turn off and this recording has been cut off. And I'm gonna try to get this video formatted and reviewed and make sure that everything has gone right before I publish this. It's been a wild ride, and I'm excited for what happens next. And I just gotta sort through. I don't even know what's going on. I'm probably not going to be the Foresight Institute videos because I can just publish stuff on my own channel. I can post this talk on my own channel, and I don't need to wait or travel all the way across the country. I think Foresight is a really good force. I congratulate them on being open and hosting talks, even if it's not whatever's happening at CDN, the super closed source, even though it's not like direct path always. The fact that what they're doing is should be encouraged, and I'll say that that's good about them, but I'm probably not going to be. I mean, let's be in my home doing whatever I want to do. So, all right, I think I should finish this video before it gets too long.